Exactly.
So we don't have to go over any then.
I don't think so.
Right, good. I'm gonna scroll then to the next chapter, next section. Bart, do you have any questions on last night's homework? That's because you didn't do it.
I did. Exceed.
No.
Wait, I have one question.
Oh, no.
Were you able to do number 1 with this method?
Yes.
Well, is it a gradient?
What was the gradient of it? 1/2 x
XY.
squared plus 1/2 y squared?
I had XY.
It was 1/2 x squared plus 1/2 y squared.
Oh, it is.
It can't be x, right? Because if you
Yeah, it is a gradient.
Yeah.
Okay. Well, I just did it out.
Then you're missing the point of the last lecture then.
Oh yeah, it is one.
Is if the force function,
Yo, how did I
force
do-
vector is a gradient, then you don't need to do all the work.
No, yeah, no, I don't know. I know what I was thinking, but I thought it had to be x, y, or just not. I don't know why. Okay, moving on.
Okay, Green's theorem. Now, for those of you following on the video, turn to page 834. This is a pretty useful one, you know. It reduces the amount of work by a lot. Okay, so a line integral taken over a simple closed plane curve can be expressed as a double integral taken over the region bounded by the curve. This result, known as Green's theorem, was discovered by George Green. He published the result in 1828. Hey, that's when the kind was elected president.
Andrew Jackson.
Andrew Jackson.
How do you know?
I guess
That's a
that's
famous question.
No, because of the E thing, huh? Remember E? How do you remember E to 15 decimal places?
Oh.
Remember 1828, 1828?
4590.
Yeah.
Something.
Oh.
Must have gone from the memory.
That's
It was
cheating.
never in my memory, Mr. Park.
Yeah, I never did
Yeah,
that.
I've never.
So Green's theorem, you can compute the work done. You can do a line integral if it's a closed plane curve. In other words, it has to start and end at the same place. You guys understand? Now some of you are thinking, yeah, but then isn't the answer just 0? No, only if the force vector is a gradient, that would be 0. But what if the force vector is not a gradient? That's why we have Green's theorem right here. So, theorem 19.3.1, Green's theorem. Let omega be a closed region totally bounded by a piecewise smooth, simple closed curve C. If this is your force function, and if it's continuously differentiable on an open set, what happened?
What?
What happened?
You closed it.
I didn't close it. It got. Is there a shortcut button for refresh?
F5, I think.
No, I didn't press F5. I don't know what happened. Anyway, here's your force vector. Then, to compute the work done, all you have to do is do a double integral over omega of the partial of q with respect to x minus the partial of p with respect to y.
Okay.
And for those of you following on the video and you guys don't have your book with you, I'll write it down on the board here. Because we're going to be using that over and over in tonight's homework. And we'll just do a couple examples. And there's another shortcut you can use here too.
Wait, how do you find area of the thing?
Double integral?
No, using Green's theorem.
Okay, wait. Can we just do these problems? Okay, so here's your force vector. I'm not going to put x and y. I'll put x and y. Force vector is p of x and y, I don't like to write the I, I'm just going to write that. And then q of x and y, j. So here's your force vector. Then if it's a closed region, then again, it means you start and end at the same place. Then to compute the work done, the integral over the curve of f of r of t, they just put f of r dot dr is equal to the double integral over omega of the partial of q with respect to x minus the partial of p with respect to y dx dy. So first of all, you got to understand when you can use Green's theorem. It has to be a continuously differentiable, or at least piecewise, and it has to start and end at the same place. So you guys understand what this is? This is your force function. So you take the partial of this one with respect to x, minus the partial of this one with respect to y. Just subtract it, and then just do an integral over omega, whatever the closed region is. Okay, so let's take a look at some examples. I think the book had one decent example. Which one was it? Which one was it? Okay, here. This is on the bottom of page 835, if you're following along. Okay, so we're going to compute the work done. So the problem says, use Green's theorem to compute the work here. The integral of C of, they write it like this, 1 plus 10xy plus y squared dx plus 6xy plus 5x squared dy. They write it like that. So you guys understand what that is?
The green theorem.
That's like the force function, the force vector right there. So that's like the x component, and that's the y component. Or this is p, and this is q. You get it? In terms of this thing. This is p, this is q. Okay? Where c, which the region is a square, with the vertices, I'm going to draw the graph here. The vertices are 0, 0, a 0, a, and 0a traversed counterclockwise. So here's the region, it's this square, and you're going to go counterclockwise. Now, do you guys remember in the very first section we had to do like 4 separate integrals? When you have something like this?
Yeah.
But now we don't have to because we got Green's theorem. It's going to save the amount of work that we have to do a lot. Okay, so what do we have to do? We got to compute the partial of q with respect to x and the partial of p with respect to y. So let's do that first. What's the partial of q with respect to x? Now this is p and this is the q, yeah? What's the partial of this one with respect to x?
6y
6y
plus 10x.
plus 10x. Everybody got that? It's easy. What's the partial of p with respect to y? So what's the partial of this one with respect to y? Come on, man.
X plus 2.
10x plus 2y. Everybody agree? So now all you have to do is subtract. Take this minus this. So we're going to do a double integral over this region of, that's a 10, yeah? This minus this. What is this minus this? I'll give you a hint. The 10x is canceled out.
y.
And you get 4y. And we're going to integrate that dx, dy over this region over here, over omega. And that will give us the work. Okay, now does anybody notice something?
It's box.
So, okay, so if you wanted to integrate this doing a regular integral, how would you set this up? If you integrate it with respect to y first, if I integrate it with respect to y, I'm gonna go from here to here. What is that? 0 to 8. Oh, so this one is like, it's not that hard, right? And then if you integrate with respect, because they do something different. Then they integrate from 0 to a here. Oh, so it's really not that hard if you just did it that way. But they notice something. Let's take this 4 and throw it outside. We forgot to write the dx there. Hey, you somebody. Where have I seen this integral before?
The centroid.
The centroid. The x-coordinate or the y-coordinate of the centroid?
Y.
The y-coordinate. So let's review. To compute the y-coordinate of the centroid doing a two-dimensional surface is the double integral over omega of y dx dy over the area of the region, right? Area of omega,
Yeah.
right? So therefore, what is this equal to then? What is just this part equal to?
Centroid times
The y-coordinate of the centroid times the area of omega. So for times the y coordinate of the centroid times the area of omega. Well, look at this region. Well, I mean, it's so easy. What would the y coordinate of the centroid be? What? How get 4? What is the y coordinate of the centroid right there?
Oh, I thought that was it. Oh, A over 2.
A over 2 times the area of this region.
A squared.
A squared. And so what is that going to be? 2a cubed.
That's what I'm thinking.
Of course, if you did, you would get the same thing if you went from 0 to a and 0 to a, but that's because this was an easy problem. If it wasn't so easy, then it wouldn't, then you have to do more things. So do you guys understand that? So whenever you see this integral, y dx dy, or x dx dy, then you want to use the centroid method because it reduces your work a lot. Yeah.
What if the shape isn't like a square, but it's like all random like
Okay, well, see, this problem is easy because the area of omega is easy to compute, that's why, yeah?
yeah.
If the area of omega is not easy to compute, but see, you would still have to do an integral anyway.
No, but I'm saying like, so if it's like not a shape like this, then you can't do it anyway, obviously. But then like, what would be like the limits of integration? If it's like,
Well, it'll be the same, like, okay, give me an example, like what?
if
You mean if this region was what?
I don't know, like
Like a parabola or something?
or like not
Not a square. Yeah, how about a parabola? How about a circle then?
sure.
Okay, what if you had this circle, x squared plus y squared equal 4? So if you're going to compute this area here, if you integrate with respect to y first, y is going to go from this to that, right? So wouldn't that be negative square root of 4 minus x squared to the square root of 4 minus x squared? Right, if you solve for y. And then you integrate with respect to x, so it's going to go from negative to 2. Remember, the last one always got to be constant, yeah?
Will it goes like shape like this or no? Like a random shape.
No, it's not going to be random. It's got to be described algebraically, yeah? You know what I mean?
Okay.
Okay, one more example and we're done. This section is quite easy. Okay, next example. Use Green's theorem. Okay, we'll use this side of the board. Use Green's theorem to do double integral of the curve. So the line integral of, you got, where is it? Oh gosh, I can't even, got the glare. 4xy plus y squared dx. So when you see this, you got to be thinking, hey, this is p plus, oh no, it's minus xy plus 3x squared dy. That's q. So what you do first, just like the last problem, compute the partial of q with respect to x. What's the partial of q with respect to x? And look at that minus sign there. It's kind of important. Partial of q with respect to x.
Negative y minus 6x.
And partial of p with respect to y, part?
4x plus 2x.
What?
Oh.
2y you mean?
Yeah, I said 2y.
Oh, okay, I didn't hear that. And so, what is the partial, what is this minus this? This minus this?
Negative 3y minus
Negative 3y minus 10x. I like to put the x first. And then all you have to do now is integrate this over omega. Why am I putting the y first, fool? Integrate this over omega, where omega is, I'm trying to read the problem. Oh, here, is the circle. X plus 1 squared plus y minus 2 squared equals 9. Notice how a circle is a closed curve, yeah? What's the center of the circle? Negative 1, 2, radius 3. That looks ugly. Okay, that's better. It's still ugly. And it says counterclockwise, but it really doesn't matter. Okay, so here we go. What do you notice? Okay, what if you split this up into two integrals like that? dx dy plus double
You
integral
have the
over
centroid
omega negative 3y dx dy. And then over here, you can throw out a negative 3. And then over here, you can throw out a negative 10. And then, hey, you somebody. Isn't that the x coordinate of the centroid multiplied by the area?
Yeah.
And then, hey, you somebody, that's the y coordinate of the centroid multiplied by the area. But that's easy because if this is a circle, isn't the centroid the center? Which is negative 1 comma 2. So the x coordinate of the centroid is negative 1 multiplied by the area of a circle of radius 3. Come on, man. What's the area of a circle of radius 3? 9 pi. And then minus 3 times the y coordinate of the centroid is 2 multiplied by the area 9 pi. And I think I can leave the simplifying up to you. What the heck, let's just do it. 90 pi minus 54 pi, is that right? And you get 36 pi. That's what I get. Is that the same as the book? Yep, 36 pi.
So is there always going to be some shape that we know is actually?
Yeah, otherwise, well, it doesn't have to be. It's just that if it's a shape that you know, then you can use the centroid method, yeah? But I would guess in the homework, maybe you're not gonna use the centroid. Maybe they'll give you some weird figure. So then you gotta ask yourself, is it easier to compute the centroid or just work out this integral? You know what I mean? Okay, I think tonight's homework is very mechanical. Let me look at the problems. Doesn't look difficult. Number 15. Determine the area under one arch of the cyclone. Did I assign number 15? I wonder why they would put that on right there. Compute the area under one arch of the cycloid. No, I'm just.
No, you didn't.
They
You
did.
went up to 11.
No, I'm just wondering why they would do that.
Oh.
I'm not sure. Okay, whatever. It's not assigned anyway.